All right. Bonjour tout le monde. Alors, je vais faire un petit peu l'introduction en anglais parce qu'on a 30 personnes aussi de l'AEU qui sont avec nous en ligne aujourd'hui. So, it's my great pleasure to introduce you to Dr. Nathaniel Dylan Kee, who's a specialist in massive star winds. And here's the massive star winds coming in. So, Dr. Kee completed his PhD at University of Delaware in 2015, specializing in the winds of massive OB stars. Completed then afterwards the first postdoc at the University of, and I need to pronounce this correctly, Tübingen in Germany, working on the formation of massive stars. So for the three main sequence after the PhD in massive main sequence stars. Then a second postdoc at KU Leuven in Belgium on the winds of post main sequence stars. And now he's working at the NSO, so the National Solar Observatory at Hawaii, trying to solve self-consistent MHD models of the solar atmospheres in order to study the properties of flares, CMBs, amongst other things. And so I'm very excited to hear this presentation, and I hope you are too. And without further ado, I'll give the floor to you.
Thank you, and thanks to everybody joining here and online. If you're, as Guillaume said, I've done a quite variety of things, so I'm today going to be focusing on the ongoing legs of work from my time in Leuven, but if any of those other things spark your interest, I'm around for the rest of the day and tomorrow here, and I'm available via email for folks online to chat about any of those other topics as well. So this is work that was launched over the past couple of years by myself and then several PhD students who I was working with at KU Leuven in Belgium about winds of post-main sequence massive stars, and particularly the physical processes behind launching these winds. So just briefly, kind of outline of the talk here, give you a little bit of context on massive stars and why we care about their mass loss. And then the rest of it will be split into mostly two parts. One on some first theoretical models of mass loss for red supergiants, and the second on numerical simulations of the winds of Wolf-Rayet stars. So jumping in here on luminous massive stars, the obligatory HR diagram to orient ourselves here. If we're talking about the sun being down here, I'm really focusing for this talk on stars up near the top of the diagram, but actually this is a little too limited for the range of things that I'm interested in. So in fact, stars that I'm going to be talking about shoot off the top and left of this HR diagram here. So to be a little bit more specific, I'm talking about stars that begin their lives on the main sequence as spectral type O and B. And then for the lower mass end of this, once they leave the main sequence, I'm talking about stars that cross the Hertzsprung gap and end up as red supergiants, or for the little bit more massive end of this, talking about stars, again, beginning over here in the blue, and then trying to evolve to the red and getting turned back, whether that's by their own mass loss being so strong that they lose their envelopes, or whether this is via some sort of external stripping, potentially by a companion. So this is a very simple picture, of course, of massive star evolution. And in fact, as is often the case, the reality is a lot more complicated and leaves a lot of open venues of study that we really want to dig into on this. To kind of give you a taste of some of the open questions here, if we go to the very most massive end, after the Wolf-Rayet star, we're talking about things that explode as supernovae, leaving behind stellar mass black holes, where theory from stellar evolution modeling and supernova modeling suggests that we leave behind roughly black holes of less than about 40 solar masses. However, recently, there was this paper that came out in 2019 where the authors claim a 68 maybe up to 70, 80 solar mass black hole, which of course kicked up a lot of reactions in the community. But independent of which side of this you come down on, whether this is real, whether it's not real, it really highlights how much, especially the late phase evolution and final fates of massive stars are uncertain, and how much we really are digging into trying to disentangle these late phase interesting objects. So for the purposes of today, I'm highlighting two other evolutionary problems. One for red supergiants, namely the supernova progenitor red supergiant problem, which we can paraphrase by saying we don't observe supernovae at locations in the HR diagram where we do expect supernova progenitor red supergiants. A little bit more specifically, if you look at stellar evolution modeling, you can get stars evolving over to the red supergiant branch here, and the upper limit of type 2 supernovae exploding from red supergiants is about here. So we have some upper end of this distribution where we can get stars by stellar evolution modeling, but then we don't see supernovas arising from them. And to compound this problem a little bit, if you look at the distribution of observed red supergiants, it seems like, so what I'm showing here is, and I'll try and use my cursor for the folks online, the gray is the distribution of type 2p supernova progenitors, type 2p being the things that come out of red supergiants. And then the colored lines are all observed distributions of red supergiants in different spectral type bins, which have been normalized, renormalized to the type 2p supernova progenitors. But independent of that, you can see all of these extend to higher luminosity than the places where we actually see type 2p supernovae. So it seems like stars do get there, but stellar evolution models tend to leave them behind there in places where they then are not observed to actually explode. The second problem that I'm going to be highlighting today is what we call the Wolf-Rayet radius or effective temperature problem. And you can paraphrase that by saying theory and observation don't agree about where Wolf-Rayet stars should be found in the HR diagram. Again, getting a little bit more technical about this, if you line up observed distributions of Wolf-Rayet stars and their observationally inferred radii or effective temperature, since if we made them a little smaller, they'd be, or if we change their luminosity and radius, we can move them back and forth a little bit. That's why this is radius and effective temperature coupled problem. But if you look at the distribution of where stellar evolution models drop you, they all are fairly far left here. And in fact, with the exception of some subpopulations, systematically hotter than the observed distribution of Wolf-Rayet stars. Now, for all of these problems, mass loss is a really key ingredient in understanding the stellar evolution modeling and understanding where massive stars go and how they end their lives and how they get to these end fates. To give just an example from the main sequence, if we vary the main sequence mass loss rates by about a factor of 3, which is consistent with the uncertainties in evolution in the mass loss rate here and the discrepancy between different theoretical models, traditional mass loss rates applied on the main sequence will follow the dashed line, and you get this loop that I talked about at the beginning, where we end in clicked accidentally, where we end in the Wolf-Rayet phase. But if you lower the mass loss by about a factor of 3, which is consistent with some new theoretical models coming out, instead you abandon stars off in the middle of the Hertzsprung gap, the places where we don't actually see the stars, suggesting that something else has to be happening later to get them out of this, this location. But again, independent of that, you can see these very large discrepancies where all we've changed in the models is what the mass loss rate is on the main sequence. And this problem just compounds when you go to the post-main sequence, because post-main sequence mass loss is generally inferred to be much more vigorous, much higher mass loss rates even than the main sequence, but is actually much less well understood. And specifically, we really have a less good grasp on what the physical mechanisms behind mass loss in this post-main sequence actually are. So that brings me to my first subset of this, namely mass loss for red supergiants. So to pose the problem here a little bit, diagrammatically, if you start from the star, trying to remember to point with my cursor. So if you start with the star on the left here, once you get fairly far out in the wind, you can get dust formation. These are very luminous stars. Dust is a great opacity source. You get a really efficient coupling, and you get a strong radiation force, which is fully compatible with the kinds of winds that we infer from red supergiants. However, you have this gap here, which may be several stellar radii, where the environment is too hot. The red supergiant effective temperature is something like 3,500 Kelvin, and you have to get quite a bit cooler than that before dust is inferred to be able to coagulate very efficiently. So you just have this gap where we don't have a force, and without this force, we just have no way to get the mass up to the place where we know we can get it away. And without some working theory for exactly how all of this works, we generally depend upon empirical mass loss rates for evolution in the red supergiant phase. And these are extremely uncertain in and of themselves. Different studies for the same stellar properties can predict mass loss rates that are easily an order of magnitude different. And we saw what a factor 3 does on the main sequence. Now we've got a bigger lever arm with more mass loss, and we're talking about a much greater uncertainty in what's actually going on. So the model that I've leveraged and what I'm going to be talking to you about today is trying to fill this gap with turbulent pressure. These stars are observed to have highly turbulent atmospheres. See what we can do with that. Presaging the fact that this actually comes out to be a fairly straightforward analytic model, I'm starting from the, we're going to go through the equations here, and I'll walk you through how we can derive a mass loss rate dependent on turbulent pressure. So from conservation of mass and momentum, we're really plucking out this gradient of pressure term and decomposing it into not just a gas pressure, but also a turbulent pressure term, where we, similarly to gas pressure, make this a mass density times characteristic velocity, a turbulent velocity, giving us an increased effective sound speed for the pressure stratification of the atmosphere. Recasting the momentum equation in terms of our insight of turbulent pressure here, and looking for a steady state in the mass conservation equation, we get down to some constant rho v r squared, and the game is we need to know all three of these things at one point. If we've got all three at one point, that is a mass loss rate by mass conservation. Taking inspiration from the solar wind, given that we've got this effective sound speed, we look for a sort of a modified Parker wind here, now driven by this combined thermal and turbulent pressure instead of by thermal pressure alone. And we we can solve for this, and then we can solve for the density by integrating back through the wind, knowing a radius of the star and knowing that that is the optical depth 2/3 photosphere and characteristic opacities in the wind. We can place where that photosphere is. And then that gives us a density, a radius, and we're doing this at that effective sound speed. So there's our velocity. We can get all three analytically. And just as a note, this is assuming an opacity of the Rosalind mean opacity. The optical depth is accumulated fairly close to the surface of the star. So it's a pretty good approximation to treat this as the opacity right up against the star. So that's all isothermal because it's using a fixed effective sound speed here. It's using, generally some fixed properties, but we can actually take that analytic mass loss and applying a temperature gradient through the wind, we can turn that into a non-isothermal mass loss. And it turns out that in addition to getting an analytic mass loss rate for turbulent pressure, we can actually also get a pretty good fit numerically just based on the turbulent pressure and the escape speed of the star to get from that analytic to a closed form numerical prediction of the mass loss rate. Now, for all of this, I've just been using the effective sound speed as a free parameter. And dragging it around, it's now showed up all over the place. Shows up in our Parker radius, it shows up, which then shows up in the density, it shows up in this fit. So we really need to know what this turbulent pressure, this effective sound speed ends up actually being. And for that, we can turn back to observations. We take a sample from Jocelyn and Plez 2007 with some recent observations by Keishi Onaka and collaborators in 2017, where they observationally infer turbulent velocities in the atmospheres of red supergiants. What we then do is taking their mass loss rates for their stars, we can invert our equation and solve for what we theoretically would need the turbulent velocity to be for this mechanism to work. And plotting this up for the whole distribution of stars, the red pluses are what's observationally inferred. The black dots are what we need from theory. So there's not really much of a systematic offset. In fact, actually, what we need from theory is a little lower than what's observationally inferred. So we're in pretty good shape here. If you prefer it as a histogram, here's a histogram of this instead of object by object. And what we end up coming out with is that on average, we need a turbulent velocity from theory, which is about 18 plus a little bit kilometers per second, which is within the error bars of within 1 sigma of the within 1 sigma of the observationally inferred turbulent velocity in the atmospheres of red supergiants. So all of that together brings us to a first theoretical prediction for mass loss of red supergiants. So I've dropped this into the figure I showed you before. Now is this pink dashed line. All right, so that's all well and good, but what do we actually, where does that turbulent velocity come from? We're sort of kicking the problem down the line. We didn't know where the mass loss came from. We didn't know what this force was. Now we've got turbulent velocity. We don't know where that comes from. But there's recent work that suggests that this may actually be a natural result of convection. I put convection in giant air quotes here, near or locally above the Eddington limit, initiating supersonic motions. And the reason I'm putting convection in air quotes here is that now it's not so much convection turnover driven by some sort of adiabatic gradient in the atmosphere. It's actually that you get a net outward radiative force inside the star. When hydrogen and helium recombine, your radiation force can exceed gravity, so you exceed, that's the Eddington limit, and you actually get a net, you start trying to drive a wind deep inside the star. And once your hydrogen and helium recombine, by the time you get to the photosphere, you've lost that radiation force and you won't regain it very effectively until you get out to the dust sublimation front. So the wind starts to fail, but you've already kicked up these giant turnovers, which are highly supersonic by the time that they reach the surface of the star. We're talking like Mach 4 or more. And that actually can turn over the whole atmosphere of a red supergiant with the sort of characteristic velocities that we need to be able to get out this mass loss that we're doing with a turbulent pressure. So to kind of highlight this from some numerical simulations recently by Jared Goldberg and collaborators published last year, the dashed line here is the photosphere of the star, and you can see that we get velocities that are kicked out. I still get velocity extending quite a bit above the optical photosphere of the star. So with this convection really not just is turning things over, it's overshooting into the circumstellar environment. And you get a pretty quick turnover of temperature. I said this before, but just to reiterate, these velocities are pretty well in line with what we would theoretically need to actually get out of the atmosphere. You see, we're getting something like maybe 15 to 20 kilometers per second here. And yeah, we also, in simulations of the star, this turnover and overshoot is not just stirring up the circumstellar environment. We actually also, the top figure now is density. You're getting a fair amount of atmospheric extension out of this too. So this seems really promising, and like these things are all really aligning quite well for turbulent velocity to be a realistic method of getting mass off of red supergiants. Now, an interesting property of all of this is that these turbulent velocities are metallicity independent. They're really driven, if this is the mechanism, which it seems plausible, they're driven by hydrogen and helium recombination. So that would say that this turbulent pressure is going to be driving for the same stellar structure transported from one environment to another, the same wind. Of course, evolution will get you a little bit of a different star, but this mechanism itself doesn't depend upon the environment that you end up in. Now, as promised, coming back to stellar evolution, if we take the standard mass loss rates in the red supergiant phase on the left, and we take ours on the right, we can get back very effectively out of the red supergiant phase. We still evolve over there, we still evolve up the red supergiant branch, but stars now can turn around, evolve back toward the blue again, and end their lives in places where we don't have this this red supergiant supernova progenitor red supergiant problem. So it seems like this mass loss mechanism really provides a promising explanation for this the solution to the red supergiant problem. Yeah, we just aren't going to populate this region up here with a supernova progenitor. Driving this home a little bit, part of the reason that our models turn back faster than those using the Diago rates, which are the traditional red supergiant choice, this mechanism has the turbulent pressure has a very strong dependence on surface gravity, and on proximity to the Eddington limit due to both extending the effective scale height. So as stars evolve up the red supergiant branch, our model predicts that they'll have a luminosity increase, but then as they sit there and they start to lose mass, their effective gravity, surface gravity goes down, they lose more mass, and this gives you a positive feedback loop that gives you a near runaway effect in the stellar evolution modeling, so that once a star arrives high on the red supergiant branch, it starts very efficiently stripping its envelope. Just you lose a little bit of mass, the envelope gets bigger, you lose more mass, on and on until the star zips on back to the blue again. Okay, so that wraps up the first half of what I want to talk about. And now I'm going to move on to talking about the other end, whether this is for the higher mass stars that have never reached the red supergiant branch, or whether it's these stars that I'm now talking about, which made it all the way over, but turned over and came all the way back again. We're ending up in the Wolf-Rayet phase. And here again, we need to talk about what the mass loss is really doing. Now, for the Wolf-Rayet phase, there's a lot less tension between empirically inferred mass loss rates. Different studies agree with each other fairly well. There's a little bit of a slope dependence. On this, I'm showing some work from Andreas Sander and collaborators in 2019. And the purple lines are compared with the standard Nugis and Lammers mass loss rates from 2000. You can see it's all pretty well in line. We're same order of magnitude. There's a little bit of a slope dependence here, but it's not nearly so bad as what we were dealing with for the uncertainty in the red supergiant phase. However, the physical mechanism behind launching these winds has been very elusive. And to understand that, if we take a Wolf-Rayet core and actually try and launch a wind from it, the winds of Wolf-Rayet stars, they lose so much mass that the wind itself becomes optically thick. And the photosphere, as observed, is way out here in the wind. So we just totally lose this whole launching region. And anything that we have to try and figure out about the star needs to be extrapolated backward through the wind. And this is actually why we can run into this effective temperature core radius problem. We don't see the effective temperature of the star. We actually see an effective temperature of the wind itself. And we're having to back out somehow what the effective temperature of the star was. So, talking about Wolf-Rayet stars, I'm now going to, rather than talking about the pressure term here, I'm really going to focus on this radiation force. Because for Wolf-Rayet stars, this seems like a really promising avenue. And I glossed over this before, but I'm actually going to need to talk about it more in depth for some of the models and how we parameterize things. And because we're talking about radiation force, a good parameter for us to use is this Eddington factor that I was talking about before, where we take the ratio of the radiation force to gravity, and because both scale at r squared, we get a parameter which is just based on stellar parameters, not based on location in, or not directly based on location in the wind. Now, for the core of a Wolf-Rayet star, these are thought to be quite hot. And so iron recombination is probably a pretty good place to start looking for how we get a wind off a Wolf-Rayet star. What I'm showing here is contours of the opal opacities from Lawrence Livermore as a function of temperature and density. And if you're coming from the core of the star and going outward, you have to get through this big old opacity bump when iron recombines. connecting this to the red supergiants, this is the helium and hydrogen recombination bumps, which were strong enough in the outer atmosphere of a red supergiant to really drive this initial launch. So we're now dealing with even bigger opacities in a region that is less susceptible to convection to begin with. So we're likely to start launching a pretty strong outflow from this. Unfortunately, if you just put in the recombination opacity, it, like hydrogen and helium in the red supergiants, dies before you can get out of the star. You get over this bump, and you can, depending on the type of mass loss you want to launch, you can either get, for high mass loss rates, very compact, strong winds, or sort of weak extended winds, but everything falls back to zero velocity at some point. You just, again, we're dealing with a missing force. So we need now, rather than a force near the star to get things away, we need the force away from the star that can continue carrying you out of the gravitational well once you've launched a wind. Once you get out into this region in the outer wind, however, you're in conditions that are very much like the main sequence O and B stars. So we can look back, how do they drive their winds? And those winds are driven by line opacity in the ultraviolet. And this is an interesting type of driving, because now we're talking about spectral lines. If we're talking about some sort of wind, keep doing this. If we talk about some sort of wind velocity profile as a function of radius, and the gray here is highlighting a region that the spectral line is smeared out over around the mean motion of the mean Doppler shift of the wind. Photons at different wavelengths, frequencies, Doppler shifts away from line center, however you want to think about this, can interact with the spectral line at different distances from the star. And since you have a lot of spectral lines out in the ultraviolet, and for main sequence O and B stars, or for Wolf-Rayet stars, by the time you get into their outer winds, the peak of your spectral energy distribution is also in the ultraviolet. So you can get a really efficient coupling here, with the interesting property that this scales now opacity scales like the velocity gradient, and inversely like density. Not to drag out the point too much here, if we tack these things together, we get a wind. So this is now a working model, and these are steady state simulations of the wind. Where on the left, I'm showing you the velocity profile, and on the right, I'm showing you the various components of the radiation driving. And this is we have this interesting feature here that we get this initial acceleration by iron opacity. You can see this is around where it fails. The wind actually starts to decelerate and try to turn back into one of these extended winds I showed you at the beginning, but we reach a low enough density that line driving becomes efficient. We get this really steep pickup in the line driving around the just below the photosphere, when we start getting low enough densities that we can actually start driving outward, and we're able to lift the wind fully out of the gravitational well. Now, the reason that this gives us some good handle on the Wolf-Rayet core problem is that when we go back and try to figure out what the radius of the star was, we don't see any of this down in here, where we had the initial launching and then the begin and fall back. If you compute the optical depth through the wind, this gray region here is all below the Rosslyn mean optical depth 2/3 photosphere. So if you try to fit the wind backward, you don't have the handle on the fact that you turned over here. You fit something that's way out here, where top axis is actually giving us a real radius. The bottom is in this x coordinate, so we can see the whole wind. But if you look at the top axis, we're 2.5, 3 times the radius of the hydrostatic photosphere out into the wind by the time that we would have inferred the core was where we would infer the core was just by extrapolating backward from the part of the wind that we can see. And if we apply this to these to this discrepancy, the plus here is the mean of the distribution of observed Wolf-Rayet stars from some recent work, and applying that factor 2.5 to 3, believe here we applied 2.5, drops us right back onto the predicted zero age main sequence for pure helium stars. So right back onto the location where we were really hoping we would be from stellar evolution modeling. So this one actually turns out it's not actually a stellar evolution problem. It's a just what can we see and how do we figure out what the star looks like problem. So that this was looked like a discrepancy, wasn't a discrepancy. So good news on that one. Everybody was right. Now we can actually also, though, we've got these this model now. We can run the simulations with it. Might as well run off and see what we can do. So we started running some multi-D simulations here too, where the left is 2D. And it turns out that this, for any given strip in the atmosphere, this turnover and begin to fall back is seeds a lot of instability in the envelope of the star. And so what we end up finding is that when we go to multi-D simulations of this, the winds of Wolf-Rayet stars become very structured. And the right panel here is a density isocontours in a 3D model, which really, yeah, I mean, we're very, very clumped, very, very structured winds. So, and in fact, actually, if you look at the central panel here, radial velocity, you can see that we have these blue regions near the star where the wind actually does fail in some latitudinal stripes. We try to launch mass, and the star actually locally can launch too much, and it doesn't get out to the front where we can actually get the line opacity kicking in, and some material actually does fall back into the star. So we're getting some really interesting dynamical processes that are predicted, although all of this is unfortunately below the wind photosphere. Comparing the mean velocity profile from this 2D model, we still actually, even though we're now very structured, even though we have all of this fallback, on average, we're getting a fairly comparable type of velocity profile in the wind, where this is then the one that we got in 1D. So you can actually see it's a little bit more extended. The turnover point is a little further out for this specific model, but morphologically, even though some streams are fully just blown straight out, whereas others are coming back, on average, we're still getting this sort of two-phase acceleration profile. And because of the funny units here, we're of plotting in x, this modified radius in the bottom, it's about less than a factor, well, yeah, less than a factor 2 discrepancy between the actual radii we get here. So this is, the 1D wasn't so bad, but now we have a better handle from 2D or 3D. Now that we don't have to worry about whether or not we can fully get out, we can play around with varying the wind strength a little bit. So if we go up in luminosity for fixed mass or down in mass for fixed luminosity, varying this this Eddington parameter, as you might expect, if we increase gamma, now we have more force at the bottom. We need less to pick us up at the top because you really can launch very strongly. And so we can start transitioning from a two-phase back to a more smooth one-phase wind. But if we go down, we actually end up with something really interesting, where dropping the Eddington factor, now you don't have enough punch at the bottom in the iron opacity. And you still end up with an extended atmosphere, but here the solid dots are the optical photosphere in each of these for each of these models, and the circles, which are all on top of each other for the top ones way down here, are the place where the wind crosses its own sound speed. And it turns out that that place where you cross the sound speed and where you get most of your acceleration is inside the photosphere if you're at high luminosity to mass. But once you go down a little bit, you actually flip that, and you still get some extended atmosphere, but the real wind driving is all happening in the visible region again. And this is leads to a much, much lower mass loss for these low luminosity stars. So this is an interesting thing that we should really follow up with looking at the low luminosity extension of stars that have gotten over to the hot side of the HR diagram to see if we can observationally back out this population that we're predicting to have low mass loss and observable wind launching radii. And actually ends up, as I'm showing here, having a bit of a different prediction than the Wolf-Rayet, the empirically inferred Wolf-Rayet mass loss prescriptions that are generally people are working on. So this is an interesting implication and a subject for some future work. And on that, I have said my piece. I'll leave you with a couple of takeaway points here that we've got the first theoretical models for red supergiant winds. These seem to be driven by turbulent pressure, providing a natural solution for the red supergiant supernova progenitor problem. And an exciting future prospect to dig into with this is this metallicity independence that I highlighted, and what this would mean in low metallicity and early universe sort of environments. Second half, I want you to take away that we've got first dynamical simulations of Wolf-Rayet stars. These seem to really be driven by two flavors of radiative acceleration, but very much by radiative acceleration. And this provides a natural solution to the Wolf-Rayet radius effective temperature problem, with an interesting future prospect that we should look into this low luminosity mass loss from stripped helium stars. Thank you.
Very, very clear and succinct presentation of this very complicated subject. So if anyone has questions, well.
Yes.
Okay, I'll leave out the Wolf-Rayet question in the last two personally.
Okay.
About the red supergiant prediction.
Yeah.
I saw that you had some red supergiants at 17 solar mountains that went back to the blue.
Yeah.
So would that be in contradiction with the fact that we do observe red supergiants? So that's supernova that should be at that mass?
So I think that,
Or is it just very sensitive to?
well, so that this, no, absolutely. It's very sensitive to the velocity. Here, let me get back to that figure. So there's a couple of pieces here. If we have lower mass loss on the main sequence, we can deliver stars over to the red supergiant branch in a different pathway. So we could get stars that would be that would look like, how do I, let me be careful about how I said this. So if we take standard mass loss on the main sequence, a 17 solar mass star will arrive to the red supergiant branch with a mass that is then comparable to what we see explode. If we start playing around with mass loss in these earlier phases, especially since we're talking about lowering it, you're delivering lower mass stars on the main sequence to the same-ish locations on the red supergiant branch. And these models all are actually using those lowered mass loss rates on the main sequence. I'm using the Björklund et al. Results for these. So if I was to have used the Vink et al. Rates, we would be talking about a little bit of a different mass cutoff. So it may not be, yeah, we can play with it, but it's something that it's, I guess actually that question really highlights the point that this all depends very much on not just individual phases, but the whole integrated mass loss of the star. And there are, of course, other levers that can move things around a little bit. For instance, efficiency of convection. That's a fairly common, since we have to do this in 1D, where that's very parameterized and uncertain as well. So
maybe just one last quick
yes.
about this.
Yeah.
I may have missed it, but what happened with the idea that the extra force is pulsation?
Oh,
I missed it, but you had it.
yeah, so the extra force being pulsations was originally more of an idea that kind of came from analogy with the AGB stars, where we do think that there's this really strong pulsational piston. For red supergiants, it's looking like as we move forward with this, that you don't need the pulsation so much just because you've got such an incredible amount of energy input from the luminosity of the star itself. And this convective turnover already generates a really extended, highly turbulent atmosphere, even before we start trying to put in some sort of pulsational piston. Mm-hmm.
We have a question online from Tony Moffat.
Yes.
So Tony,
Hi, Tony.
turn on your camera and say it yourself.
Yeah, right.
Oh, 1 second.
Hi, Dylan. Sorry I didn't make it to your talk, but I am at home. And it's a pleasure to hear an update to this vexing problem that's been around with us for a while. You did mention, though, something I found a bit strange, perhaps, was that the red supergiants should behave independent of metallicity. Yet, isn't it true that we see more red supergiants, relatively more, at low metallicity? I thought that was a fact of observation.
Yeah, and I think that this is definitely a vexing problem, but I think that you can explain this also by main sequence mass loss, because you're going to have a harder time stripping the envelope, at least for a single star evolution. If you have lower metallicity and lower mass loss on, because the main sequence mass loss will still scale with metallicity as we expect. So you're going to not be able to get the luminous blue variable to Wolf-Rayet turnaround as early, perhaps, for low metallicity environments, meaning that they would sort of get tagged onto this this tail that I showed you at the beginning, where we observe the red supergiants, but they go away before they explode away from the supergiant branch before they explode as type 2p supernovae. At least that's my hand waving thought on it right now.
Okay, well, that's interesting. If I could ask a second question about Wolf-Rayet stars.
Yes.
Over the years, we have found clumping in Wolf-Rayet winds, and I'm wondering if the pressure from that could be a contributing factor to driving the winds, just the pressure of the turbulent pressure.
So I didn't talk about this element, but when we do the multi-D modeling, it turns out that there is a considerable momentum redistribution from the optically thin, from the low density to high density plasma, and by ram pressure. So we are actually accelerating the material in between the clumps a lot, kicking it into the clumps themselves and accelerating them out by kind of hitting them from behind. We're not finding, though, in general, that there's a lot of the other forces are so strong that it seems like the expansion of the clumps by their own internal pressure is not as important for the dynamics of the wind. Not to
Okay.
say it's not in there, but it's
Yeah,
maybe subdominant.
okay, that sounds reasonable. I see Joe Pulse is waiting to ask a question too. Hi, Joe.
Oh, yes.
Just open yours, remind me, like this, it's open.
Yeah, you could just,
Does the referee agree
should
that
have,
I ask a question?
it doesn't matter, just, yeah.
I thought I had sound on here.
Oh,
Hello, Dylan, can you hear me?
okay, well, we can look at it.
Yeah,
Okay,
my,
the words, so we know.
yeah,
Just-
my computer's
so,
not,
Yeah, so just let's
yeah, that's
not
fine.
talk over each other. So now, Joaquin Pulse.
Okay, so Dylan, can you hear me?
Yes.
Okay, Dylan, thanks a lot for this excellent talk. It was very concise and very clear. So I'm really excited. Good, I have a question to this turbulent pressure. The first one is a very quick one. Can you tell us how you said the turbulent velocities are observed? Is this observed from line broadening, or how do they observe the turbulent velocity?
So yes, it's part of it's from line broadening. There's also I think from the, if I recall correctly, from the Jocelyn and Plez paper that I showed, they are observing different spectral lines at which would be forming at different depths and trying to get a little bit of a differential picture of velocity dispersion between different temperatures and different line formation regions. And those seem to have an offset from each other in the Doppler velocity also, so that there's potentially some sort of extra factor in there. But I think line broadening in general, I think is a pretty good way of thinking about what they're how they're getting this out.
Good. Now I have a second question, which might be a bit more complicated, though technical. And the problem is the following. I mean, all this looks very nice, and particularly your consistency of the values you are requiring, say 17 kilometers per second, are very much in the ballpark of the observed, whatever they are, observed velocities. But now comes my question. I mean, when you make a relation between turbulent velocity and turbulent pressure, there is this famous factor 1/2, which some people apply and some people do not apply. And the factor of 1/2 here would translate in a different strength of the thermal of the turbulent velocity of a square root of 2. So, and then the consistency would no longer be so good. So can you answer on this?
Right. So the 1/2 or 1/3 or these extra factors that are coming into turbulent velocity, they would be accounting for anisotropy of the turbulent pressure or isotropy if you're going to 1/3. And it seems like we should be, my intuition is we should be on the lower end of that, because the turnover itself is being driven from below by radiation pressure. And so the dominant, turbulent is maybe not the best way to think about this, because we're not really generating a turbulent atmosphere. We're generating an atmosphere with a strong velocity continually hitting material in the atmosphere from below. So that would tend to be more anisotropic and probably lower on that extra, or closer to unity rather, on that extra factor out front.